بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولى و نعم النصير. We continue our discussion about spatial motion description in this last session in the chapter. Today I will talk about general motion of the rigid bodies and also homogeneous transformation. As we talked about it last session, a general motion of a rigid body is composed of a translation plus a rotation. And Schall theorem goes back to 18th century, state that the most general rigid body displacement can be produced by a translation along a line, which we call the screw line. We have already defined that, followed by a rotation about the same line. So it has an intuition in it that the same line that we introduced as the line of rotation can be considered as the line that the translation is being applied along with. So I will give it to you in two stages. The first stage is just don't consider this line and just to have a simple version of that the general motion is a rotation plus translation. So if we have two states of a rigid body, I just need to bring something here to show you. For example, consider that a system, a rigid body that is in the first stage, and then it is moved in the second stage. It is from here to here. So we get a snapshot from here. As we mentioned before, we put a coordinate state on it, and we just forget about the rigid body and are talking about the coordinate frame. So the coordinate frame, which is, let's say it is along this three axis here, has moved both translationally and rotationally. And this is instantaneously being changed. So at any instant in time, consider that we are now here. From here, we are now to here. Now, at this stage, we have a translational motion plus a rotational motion. As you see here, we have about 90 degrees rotation for this work. And this translational and rotational can be considered as the main part of the motion representation. And in terms of mathematically representing this motion, we can say that, okay, all the motion should be considered with respect to one frame, which we usually consider the fixed frame A. So this rigid body was oriented at the center of this fixed point frame A at instant 0, and now it is changed to this position with UVW frame. And this UVW frame, as you see, has a translational vector in space, a 3D translational vector in space that you see here with POB with respect to A, P of the origin of frame B, POB, the origin of frame B with respect to A. So this gives you basically translation, not along a line now, forget about the line, but it is a translational vector, plus a rotation. The rotation is the pure rotation that we represented by rotation matrix, quaternion, Euler angle, screw axis, or anything. And as we saw, in any representation that you use, you can forward it into a rotation matrix. No matter what kind of representation for orientation you consider in your case, I prefer to use screw axes. I will explain why, but it doesn't matter in any way. If you are using quaternion or you're using Euler angle, you can find a rotation metric representation for the orientation. And if you have these two, the orientation with the rotation matrix and the translation with a simple vector, so any point P in this rigid body can be represented from, if it is a rigid point in this rigid body, P with respect to B, this is very simply measured, and it is a constant value P of with respect to B, because this is an embedded point in the rigid body. So this can be simply measured, but since we are moving in the space, this vector, the P of the vector P in this, this is the relative, let's say, position of point P with respect to its center point or its origin frame. The absolute value of P, that we call P with respect to A, can be simplified by this vector addition. And this vector addition is PB plus POB. But these, both of them should be represented in the same frame. That's why we call P with respect to A is P with respect to B, which is by the rotation map, as we called before. It is translated into the frame A. This is P with respect to B, which is written in frame A, plus the translational motion that we call POB with respect to A. So now we can conclude or add the two parts that we discussed last session, the position separately and the orientation separately. We talk about only pure rotation in the previous slide, but here we have a general motion, rotation plus orientation plus a translation. This is a vector form. And in robotic, as I mentioned, we would like very kindly to have matrix representation and notational variation. We can define a new matrix, a 4x4 matrix. We call it homogeneous transformation matrix, that includes both of these two together. If we design a translational matrix, we call it T with respect from B to A for a general motion, not just for a rotational translation. This is a map, a matrix that can map from one frame to another frame, but now the frames are moving freely in the space, having translation and orientation. It has a 3x3 matrix within it, which we call RB with respect to A. And it has a vector 3x1, a vector POB with respect to A, and we add 3 zeros and 1 here. And if we consider this 4x4 matrix, then if we add one auxiliary, since this is 4x4, it should be multiplied by a vector which is 4x4, 4x1, not 3x1. We add another one, an auxiliary one at the end of the vector POB, on the vector POB, then we can have the same similar mapping that we have with a 3x3 rotational matrix for pure rotational map. Instead of using a vector space here, we can have a simple homogeneous transformation for this system. So PB can be represented into from frame B to frame A with respect to a translational or homogeneous transformation matrix, which is defined by this case. As you see here, we usually, because we are using different books in the context of this course, some books represent TB with respect to A with a superscript at the right-hand side. Some books use both B and A at the left. No matter what, because we are using both rotation. The important thing is, as you see here, like the rotational matrix, you can just cancel the B. If you want to represent B from frame B to A, you should put a transformation which cancels the B and goes to A. And this consists of two parts, rotational part and translational part. I will talk about this matrix in the next slide in more detail, but here we are defining a new matrix, a new notation that can simplify this vector form. And we would like to have more arithmetic and more mathematics defined on matrix manipulation rather than vector manipulation. Is it clear up to here? I can continue now to the Schall theorem. Schall theorem is a bit more than that and says that don't use two separate vectors, just use the line, the screw line. Schall theorem can be represented in this form. And this is, don't look at a very sophisticated picture here. It is quite simple. It shows you the concept. It says that this we have a screw displacement now. Up to now, we have this defined a screw rotation for a pure rotation map. But it says that this screw can be used for both rotation and translation. And that's why we are using the word screw, which is translated in Farsi, we call it piche. Piche, or screw displacement, something like a peach, or something like a screw and bolt. When you have a screw and bolt, when you rotate the screw, the bolt will go up and down. So you have both rotation and translation somehow. And this is the true meaning of the piche or screw displacement. It means that a general motion is consists of, please accurately consider my point, and I will explain that in Farsi as well, that I make sure that everybody understood that well. It is telling us that we have the general motion. It is a rotation and translation, but both of them are, the rotation is about a vector, a line, which we call it S or S hat as before. Since we know that, we have proved that this is some sort of rotation that we are using here. And there is also a translation along this vector. And to do that, we represent the rotation with the S hat and theta, as we had it before, the axis of rotation, which was the eigenvector of the rotation matrix, the true eigenvector. The angle of rotation was the value of the complex eigenvalue of the matrix, and we give you some formulation how to find that, plus a new thing, we have another four tuple here, quadruple, or four parameters here. We call it another vector, S0. S0 is exactly the same thing as POB with respect to A. How far is the origin of frame B with respect to A? Here we call it POB, as you see here. Here we call it S0 to have a translational form as we have here. I would like to ask everybody, please, since we have put you as a presenter in the slide, please don't change the screen during my presentation, because when you are changing the screen orientation, it will be changed for everybody. And since we are taking the video of it, it is somehow interrupting, and it will interrupt me too in terms of discussion. Please don't touch the chat box and the thing. And I would like Muhammad Jawad to return everything to the original frame, and please don't touch the boxes that we have here. Again, I will go through that. It is good to repeat this again. We have a presentation with a screw, 4 parameters for rotation, a vector S, and theta, the angle of rotation, and we have the translational along S. We call this vector POB, we call it S0, the vector S0, and we can basically project this vector onto this line S hat. The projection of P0 onto this line is called D. This is a distance that a bolt will go up in a stream, as you see in a screw form. So we have 8 parameters here, 4 parameters for rotation, 4 parameters for translation, and everything is along S0 with 2 constraints. This is not really 8 parameters, it is only 6 parameters. As we see, this 4 parameter, S is a unit vector, so S transpose S hat is equal to 1. So this is a rotational vector, as we see here, but this is one constraint. And the second constraint is that D, the parameter that we are considering here, it will relate S0 to S, will relate the translation along this line, and we can say that D is the projection of S onto the vector S hat, and so forth and so on. We can say that S0 transpose S hat is equal to D. Zahra is asking that can I just make it a bit larger? Do it, and we will see. If we see everything, everybody is saying that it is enlarged, then there is a problem. Well, I don't think this will happen. But please don't change the chat box and so forth. Because this part is very important. I will translate, I will speak in Farsi as well for everybody to make sure that everything is understood well. قضیه شال، چیزی که قضیه شال میگه که یک حرکت جنرال در فضا، یک حرکت عمومی در فضا توسط یک اورینتیشن یا تغییر و جهتگیری، تغییر زاویه about در واقع در حول یک محور انجام میشه، به اضافه حرکت و جابجایی خطی در امتداد همون محور. این بسیار بسیار عجیبه که این موضوع در سال 1800 تقریبا 1760-70 این به این شکل understood شده و هنوز برای ما یه مقداری سخت درک اون. البته سخت نیست، وقتی من توضیح میدم خیلی جالبه که ما میتونیم این ترنسلیشن رو و این حرکت خطی رو در امتداد همون محوری که چرخش رو قبلا تعریف کردیم در نظر بگیریم. چگونه این کار رو میکنیم؟ به این شکل انجام بدیم. میگیم خب روتیشن رو قبلا تعریف کردیم، اگه یه چرخشی داشتیم، یه روتیشن ماتریکس داشتیم، از آیگن ولیو و آیگن وکتورش میتونستیم محور اصلی چرخش و زاویه چرخش رو پیدا کنیم. همون رو پیدا میکنیم. پس ما محور چرخش رو الان داریم. حالا که محور چرخش رو داریم، میتونیم این ترنسلیشن، این حرکت خطی رو که با بردار POB نسبت به A معرفیش کردیم، اینو میتونیم در واقع تصویر کنیم روی این محور چرخش. به این ترتیب میتونیم اینو به عنوان یک مهره در نظر بگیریم، پیچ و مهره، که سیستم اینجا بوده، اگه ترنسلیشنش رو در نظر بگیریم در لحظه اول اینجا بوده، حالا حرکت کرده مثل مهره‌ای که ما پیچوندیم، انقدر چرخوندیم ولی یه پیچی داره با گام دی. وقتی ما اینو به اندازه تتا میچرخونیم، این به اندازه دی از این نقطه حرکت میکنه میره این بالا. پس ما پیچه رو تعریف میکنیم به این ترتیب با 8 پارامتر، 4 پارامتر در رابطه با اورینتیشن هست و 4 پارامتر در رابطه با حرکت خطی، 4 پارامتر حرکت زاویه‌ای، 4 پارامتر حرکت خطی. اما واقعیتش اینه که 6 پارامتره. چرا؟ چون 2 تا کانسترینت یا 2 تا قید هم داریم. در واقع بردار اسحتمون بردار یکه هست، چون بردار یکه هست نرم اون یک هست، رابطمون اینجوریه و در واقع این ارتباط پیچ و مهره‌ای که اینجا صحبت کردم، این اندازه دی که ما اینجا صحبت کردیم، این اندازه دی در واقع پروجکشن اسحت هست در امتداد اس. برابر اس ترانسپوز اس یه برداری خواهد بود که اندازش دیه. اس حتمون یک است ولی اسمون اس صفرمون به هیچ وجه یکه نیست و این اس صفر خیلی خیلی بردار مهمیه که ما باهاش خیلی مفصل روش کار میکنیم. Okay, now that we define the screw displacement, we can use that furthermore, and this is the one importance of screw representation. A rotational matrix cannot be that well. As we see, we should put it in a transformation matrix. A quaternion representation or Euler angle does not have the power to represent the general motion, but the screw displacement has this. Now, how to go from one representation to another? This is also very simple. We just use the Rodriguez formula as we used before. I have given you this part of this representation. Suppose that the screw parameters are given and we would like to find the homogeneous transformation TB with respect to A. The rotation matrix has been given before. The translation will be given by these 3 equation that D is, as you see, is presented in here. But vice versa. If we have the homogeneous transformation, it is very, very easy to find the screw axis because from the translational, from the rotational part of it, if you have the rotation matrix, just use the eigenvector and eigenvalues, or use the formulation that is given on slide 28 to find the Sx, Sy, and Z with respect to time. And then S0 and Td is very simple. S0 is POB with respect to A. This is just another representation. We call it S to represent it as a screw. And D is very simple, just the projection of S0 to S. So we can easily find these 2 parameters if the homogeneous transformation is given. The inverse problem is a bit more in detail and it is difficult, but we can have it that way. I reshared that because my screen has been freezed here. I hope that you are seeing the slide. We are now on slide 44 and you can see slide 44. Now, the general motion, let's give an example here. I assume that a transformation, a homogeneous transformation is given. How we can find the screw displacement? We first think of the rotation matrix, either get the eigenvalue or eigenvectors, or go to the slide 28, the formulation is there. You can find that this is a very simple rotation with pi over 3, 60 degrees rotation along a line which is 1, 0, -1. It is a simple line in the space. Of course, we have made it, normalized it to have a unit vector here. So we have a finite rotation of 60 degrees along a line. And from this part, as you see, this gives you the S0. This is quite easily give you the S0, and you just multiply these two together, dot multiply or project this S0 to that. You find that there is a 2 meters motion in the screw displacement, and we call this a pitch, or the amount of motion that we are using. We will use this screw displacement a lot in the next slide, so please reconsider that and try to understand it quite well. Now, and a few words about Michel Frollal-Schall, which has been born in 1793 and 1880. It is after Euler, of course, and as you see, the pictures at that time were quite rigid and with no smile, but now the people try to have more smiley pictures here. You can see how it has been working. It was working on geometry a lot, and I appreciate his understanding about the motion and how he has put this together. Now, let's talk a bit more on homogeneous transformation. The homogeneous transformations, as we talked, is a 4x4 vector. And please completely read this from my book, a detail from a parallel book. Some more detail are given there. But usually we said if we have a consecutive transformation, suppose that instead of just 2 frames, we have 3 frames, 4 frames. For a serial manipulator, we have a number of joints and frames, so we have a number of consecutive frames. And we can transform a vector from C, we can transform it into B, and then we can transform it into A. So this can go to this through T with C with respect to B, and from here to here, from B to A. And shorthand notation, as you see, P with respect to C can be, eliminated C, eliminated B, and get to A. So we can have P with respect to A by 2 transformation multiplication, as we discussed it in Euler angle as well. The rotation matrix, if you just multiply this, these 2 will be multiplied very simply as we had before, or C with respect to B, or B with respect to A, just simple multiplication. But in terms of the position should be 1 by 1. So if you put it into vector form, it is becoming a bit larger to find in terms of the vector form. So we usually use the matrix manipulation, and since MATLAB is very good for matrix manipulation, we can have this part quite easily for you. What about inverse transformation? If you have a transformation, homogeneous transformation, B with respect to A, how we can find A with respect to B? We talked about the rotation part quite well in the properties of rotation matrix. We showed that the inverse of a rotation matrix is its transpose, because this is an orthonormal matrix. So we use a transformation here, but for the vector part, we can use the inverse kinematic here to say that if we are inversing from going from here to there, we have a vector in the other direction, so it will be minus POB with respect to A, which is basically represented in the frame B, and from A to B, if you would like to say, we should have our A to B, which our A to B is basically the inverse of our B2 with respect to A, or the transpose of our B to A. So we can use this vector notation, or simply inverse the matrix. Of course, it is much easier. If you are doing it by hand, it is much easier to use this formulation. But if you are using computer, you don't need, you just inverse the homogeneous transformation. And the proof are also given in here. I would like to mention some few words about rotation matrix problems as well here, which we don't have it in screw axis problem. I don't know if Ali is with us or not. If Ali is here, please just, yeah, we have Ali here. Ali Jan, خوب توجه کن. Ali is not very keen of screw representation because he is more familiar with other representation. But I would like to try to emphasize the importance of here. In transformation arithmetic, now consider that we have two consecutive motion, one but finite angle. Let's say 30 degrees in one direction, 60 degrees in another direction. Is this arithmetic, can we have this rotation? Can we change the rotation? Is it commutative? Can we change, instead of going, since we know in a vector manipulation, we have the commutativity properties. We can't change the order. If we are adding two vectors, it is not important to add first one to the second one or second one to the first one. But in matrix manipulation, this is important. The order is important and you cannot change. It means that, let's say, that we have a rotation matrix, we have a theta angle, as you see here, around about x. We first rotate the system around x. Let's say this is good if we can have, let's say we have x, I should show you x, y, and z. So we are rotating around x, and the angle I should give you is 90 degrees just for your case. So we have about x angle, we have 90 degrees, we will rotate it 90 degrees, and then this was x, y, and z. The z is this way. And then 90 degrees along z. As you see along z, so we have here x, y, and z. From x, we rotate it 90 degrees, and from z, we rotate it again 90 degrees. From here, we are coming to here. Now, if we change the order, now instead of changing from x direction, now first rotate around z axis for 90 degrees. Now from x axis 90 degrees. It is completely different, this rotation to this rotation. This means that the order of rotation is very important, and we have many problems in the literature that are mixing this. Of course, not the new papers, but the old version. Euler angles are not interchangeable. You cannot interchange the way that the Euler angles are having been measured. So, and this is proven here. It said our x to our y gives you this way, but if you change the order as I showed you, it will give another vector. This is 0 here, but this is not 0 here anyway. So if you have finite order of rotation, they don't commute. What about screw axis? Ali John? Can you contribute, Ali? What about screw axis? Screw is a vector representation. And they can commute. It is unbelievable. The only representation which has a vector form is a screw representation. It is piche, not other thing. Anyways, how this will go if we don't have finite angle rotation. We have infinitesimal, very small rotations, then the problem is solved. If instead of having theta, we have d theta, I guess we have it here in the next slide. If we have very small angle rotation, as you see, instead of having theta, the same previous version that we have here, our x and our z, we have our x and our z here and our z and our x here, but instead of theta, we have delta theta. The thetas are very small. If we have very small angle, and as you know, when they are small, the multiplications becomes the order of 2. It is much more smaller. So we can neglect the multiplication, and this 2 becomes the same. Here we have 0. We don't have 0 here. But since this is multiplication of 2 small angle, and this is much, much smaller than 1, then we have this. What does it mean? It means that the rotation matrix, in terms of the derivatives, when we are talking about infinitesimal rotation, in terms of virtual work, we will talk about it later, or in terms of the derivative of rotation matrix, we solve the problem. But in terms of angle, the finite angle, we should take care of the order of rotation in here. Here, let us give you another example, very simple example. Consider the following rotation matrix. Suppose that the rotation matrix is given. It is not very well understood what is this rotation matrix. Is it correct or not? If it was a screw axis, it was much more understandable. So it is 30 degrees, rotation along somewhere, or 25 degrees along somewhere. We could understand, but here it is not very well understood. But we will work with that, and we would like to say at POB or PO1, 1 and 0 instead of A and B. We are using the numerical index here. PO1 with respect to 0 is 2, 1, 0. So we have a translation as well. We have a rotation and we have a translation. We want to find the inverse of this rotation matrix, T1 to 0, somehow from this rotation matrix. If we look at this, first of all, we see that what is given here is not an orthonormal matrix. This is not right. So there is a mistyping here. And what is, if you see at R12 here, if you look at this vector, the norm of this becomes more than 1. Oh, this is wrong. Something is wrong here. And again, if you look at this part, the norm of this one is also more than 1. And we know that the norm of all vectors and rows in a rotation matrix should be 1. This means that this part is wrongly mistyping. And if you check at that, you can simply find, if we know that this part is wrong, we know that the cross multiplication of these two vectors from the rotation matrix will give you this one. We can simply find that 0, 1, 6, 7 is wrong, and you should replace it with 0, 0, 6, 7. It is just a mistyping. It is quite possible to do that. First of all, we evaluate if this is given right, where we see that this is not right. Then, since we have this, and we would like to have 1 with respect to 0, then this is wrong. We would like to have 0 with respect to 1. This is the question. We would like to find the inverse problem. I will check that as well. So if we would like to have 0 with respect to 1, we should find the transpose of this matrix. We give the transpose here, and also we can multiply it here, or we can add P here, make it a 4x4 matrix, and find simple matrix inverse. But a 4x4 inverse matrix, doing it by hand is hard, but this can be easily done by hand. We can find a matrix manipulation quite easily with hand in this case. This is also another notation that if the rotation matrix is given to you, or maybe a screw axis is given to you somehow, some people have measured, and the screw axis, the axis S is not a unit vector. Because you should make it a unit vector to make the manipulation that we talked about it to be accurate. Now, this is what I would like to complete with the first session. And if there is any question, please kindly interrupt me before starting the new chapter. Any questions? Now let us talk about the real stuff.
One.
Yes, please.
For further practice, which references preferred?
Actually, the context here is mostly given from Craig's book and my book, basically the two books that I represent to you, Craig and Pararobot. But I would like to refer you to my book because it is somehow replaced that. Craig doesn't have a good treatment on screw axis. Tesai book has very, very better treatment of this case, and there is a new book written by Niku, another Iranian fellow, which is a roboticist in the United States. Niku, the new version of book of Niku has also treatment of screw axis. But for now, for this case, I think it is much easier to follow my Pararobot book, the chapter 2 of my book.
Thank you.
Okay, we now want to go to kinematic analysis. In this chapter, I will give the book alongside with the notation because we are using different books, and I will give the which book from which book you can get that. Of course, there are not all the things that I'm telling you are not fine in the books. There are some intonations that we can have among these books. Now we would like to go through the kinematics. As you see here, kinematics gives you some representation of the robot workspace, how it can work in the space and go forth and go on. And I hope that you will be finding a very, very interesting robot that I mentioned in the first slide, the SSRMS, which has a very, very long workspace. Each link of this is about 11 meters, so you have about something about 20 meter workspace with this very large manipulator in space. What we'll discuss here, it is only 3 sections, but the sections are more elaborated. I will give a very short introduction. What is kinematics? And then we go through the forward kinematics solution, and which is a simple problem. We discuss 2 ways or 3 ways to do that. And we would like to have some more emphasis on screw and screw and screw again. And then we would like to then go to the inverse kinematic, which is more elaborated and more technical in terms of the system. I can say that only this section, only kinematic analysis of a robotic manipulator could be a 3-credit course. It can have so many materials in here. But since we would like to go further in a more control aspect or more dynamics and control for the robotic, I make it as small as possible to have further development in Jacobian and dynamics. In terms of definitions, let's see what is kinematics. Kinematic, in Farsi we call it cinematic, not kinematic. Cinematic is the French work of kinematics. Kinematic analysis is the study of the geometry of motion of a body. We are considering the geometry of the motion without considering the forces and torques that cause the motion. We are not talking about how this motion is happening and how much force and effort we should put to make this happen. We just consider that the motion has happened and we would like to describe the motion. So, this description, what does it mean to describe this motion? Just bear with me, I will describe it. We are focusing on serial manipulators. In a serial manipulator, usually we have articulated structures, some joints and links that are, as we see before, that are along each other and it is articulated. So what we can call, we have a single kinematic loop. We define the loops, the kinematic loops in the beginning of the last chapter. But in a system, in a serial manipulator, we have a single kinematic loop which is open. It is not closed, it is open. We have a number of links and joints. That is quite easy. And to make the life easier, we just work with the primary joints. As I mentioned, the primary joints are either a revolute joint or a prismatic joint, where what we can say there are just one single degree of freedom. Of course, not all of the robotic manipulators are there like that. Of course, 99% are like that. But in serial manipulator, we have usually simple joints and simple actuators. As I mentioned, actuation in 2 degrees of freedom is a bit hard. What we are doing, what we are seeing in our eyes, that we can motion in this direction and in this direction with a pair of 2 muscles with our eyes. This is not very easily done in handmade, human-made robotic system. Usually we use 2 actuators and 2 single joints. But either, in the case, consider that we have a spherical joint or we have some sort of U joint or C joint, we have other compound joint. We just put them, if we have a U joint, we know that a U joint is basically consists of 2 rotary joints. So we put 2R instead of U. Or if you have a spherical joint, a ball and socket joints, we put a 3R there. So considering that this is the case with primary joints, then we can, the kinematic means to write the kinematic loop closure. The idea of loop closure is to put everything together and have a kinematic loop. What I will show you in the next slide, but just to show you how to do that, so consider an articulated joint. From the base, we have first joint, second joint, and so forth, and so we can vector represent the joints together, vector 1, vector 2, vector 3, vector 4, 2 vector n. The vector n is the end effector point, which is of our interest. And this is the one kinematic loop. It is open. We can add a vector from the base to the end effector to represent where you are, where is the end effector is actually with respect to the frame, to the base frame, which is of our interest. And this loop can be closed. We can have a consecutive order of vectors in one link of this loop and one direct vector that gives us the position and orientation of the end effector. And this is kinematic. If you put this loop closure, if you write this in 2 forms, gives you the relation between what is happening in the joints and how we can get there. In terms of kinematics, what we can call it, we can say that where the location of the end effector is, we call it a task space, the variable of task space. An end effector is in the space, it has a position and an orientation. So in a most general form, we have 6 degrees of freedom here, a position and an orientation. And we know that we can represent the position and orientation in space with a rotation matrix or with a with a homogeneous transformation, or much better in terms of a screw representation. So we have a number of degrees of freedom at the end effector, but this is one link of this loop. The other link of this loop is the joint space variable. If we would like to reach to here, what is the angle that I should use in my joints here? If I'd like to see here, the angles are different than here. And this, the angles that I have in my joints, we call it joint variables. And the relation between the joint variables and the task variables are called kinematic. But consider the main interesting thing is the kinematic loop. So, in any serial manipulator, let's say a 3 degree of freedom RRR manipulator, we call it spatial, but spatial, we call it elbow manipulator. This manipulator has been used in many robotic applications. We have 3 degrees of freedom in KUKA, in ABB, in Stabli, many robotic systems that the first 3 joints are usually a joint that is moving in the space, and then 2 arms like our arm in that can give you reach. As you see here, we have some sort of notation here. This notations, this figure is taken from Spang book, shows you how the rotation is happening. And let us now talk more kinematically. We have a kinematic loop. So in terms of joint space variable, we see that at each joint we have 3 rotational axes. So we call the joint variable with Q. We just use it Q, not theta. Q, since this is 3R, we have R1, theta 1, theta 2, theta 3. 3 angles that can change and can change the orientation of the space. If these Q1s, since we are using primary joints, if we have, instead of a rotational rotary joint here, we have a prismatic joint, then this theta would be changed to the DI, some sort of translational motion that we can get in a translational joint. So in Q case, we have either theta or D, and that's why we are using a parameter which is a generalized form of motion, either rotational motion or prismatic or translation. And we don't use any other case here because we are using just the primary joints. So how many joints we have? 3. How many joint angles we have? 3. And what is the size or dimension of the joint variable? It is 3. So we have a vector of 3 by 1. We put it in a vector form. You see that we have the transposition. Now, forget about the joint. Look at the end effector. Now, we have an end effector for an elbow manipulator. With the elbow manipulator, how can we go in that space? With the elbow manipulator, we can reach to any point in the space, X, Y, Z, within the workspace. So we call it a script X. This is a chi notation. A script X, not a usual X, a bit different X. Intentionally, I make it a bit, deformed. This is another vector here. Of course, here is X, Y, Z of the end effector. X of end effector, Z of end effector, and Y of end effector, and Z of end effector. Since it is 3 degrees of freedom, you have only 3 independent space here, which we call it X. This is very simple. So what is kinematic? The kinematic is the relation between the joint space variables. 2 task space variables. We have the Q's here and we have the X here. If forward kinematic, what is forward kinematic? If Q's are given to you, if the joint space variable are given to you, and you would like to find the task space, means that I know that my angle here is 30 degrees, 20 degrees, 40 degrees. How large I am reaching, what is my XYZ, where can I reach this? Can I get this cellular phone? Can I get to this point or not? If thetas or Q's are given, if the joint space are given and you find the task space variable, we call it forward kinematic, which is quite forward. And it is quite easy to do that in serial manipulator. And the inverse map, if X is given, suppose that we would like to reach to one point, one particular point, which is very important. We would like to make the drilling or something or painting. You see that the application that we have in robotic. So what should be my joint angle? Because I have the control on the joint angle, not on the end effector. And this point, if this is given, and we would like to find the Q that will reach to that point, we call it inverse kinematic. And we show that this problem is a bit more in depth. And we make this in two sections. First, we consider the forward kinematic, and then we go to the most challenging part in inverse kinematic. And we have to do it for a number of robotic manipulators. So, we start with forward kinematics, and let's start with a very simple one, with a motivating example. And the way I am teaching here is quite different than the way Craig is doing or other books are doing. You should know the concept, you should understand the concept, then it is much easier to follow the mathematics. What I say is, let's see what is the kinematic loop. So the simplest possible robotic manipulator that we have has two links in a plane, two joints, two rotary joints. We call it RR manipulator. One rotation here with a length of L or A, we call both of them. Another one with an L2 and theta 2. The theta angles are measured from incrementally. This is from the base and this is from the second version. So we have two angles, two rotation angles, two Q's here, and we reach to a point. Since we have 2 degrees of freedom, we can have X and Y in a plane motion. XE and YE is the X variable. As you see, the chi variable, it should be somehow script here. As we see, we denote Q by theta 1 and theta 2, and chi, or the script X, by XE and YE. And we assign a frame. We should have the motion with respect to one frame. We put a base frame, a 0 frame. Usually we call them 0, 1, 2 instead of A, B, C to have the consecutive motion better represented. So we have X0 and Y0, and we have something like that. Now denote the link vectors with the red vectors here, and the end effector vectors, the final vector with the blue one. You see the loop closure here quite easily. A vector formulation can be written. The blue vector is the task space, the chi version. The red one is the joint space variables, is the Q version. And we know that this vector is equal to the addition of these two vectors. And we write this vector notation here, either in a matrix form or in a vector form. Right now it is very easy. What is the loop closure? What we call it loop closure. We close the loop here. Very simple. We put one loop in task space, one single loop in joint space, and then we close them together. We add them together. It is quite easy. As you see, this is the loop closure. We call L1, the vector L1 plus the vector L2 is equal to vector of, we call chi. This should be changed to chi. The vector, the script X. The script X vector is this one. As simple as that. No notation, no nothing. For now, nothing, no notation. And what you see, what is L1? L1 has two components, X component, Y component. This vector, since we are in a plane, we can represent it into two components. We can have it component-wise. So the L1 cosine of theta is this one, L2, this part, cosine of the absolute angular value, that is theta 1 plus theta 2. L2 cosine of theta 1 plus theta 2 gives you the XE. And L1 sine of theta 1 plus L2 sine of theta 1 plus theta 2 gives you YE. And this is forward kinematics. That's all. The loop closure gives you the forward kinematic. What does it mean, forward kinematic? If theta 1 and theta 2 and the parameters of the robot, which is the length of the length, and the structure that we are using, which is our manipulator, is given. If theta 1 and theta 2 is given, you can easily find XE and YE. See here? If Q is given, we would like to find X of E and Y of E, and this is done quite easy. No need to have sophisticated manipulation. Very simple loop closure method. Of course, this is a simple robot, so the vectors are very simple. If it is more complicated, you need some more intuition and so forth. We will discuss about that later. We have a shorthand notation, since robotics is the science of notations, to make it somehow more comprehensive and shorthand. Instead of writing cosine of theta 1, we call it C1 or C theta 1. In the books, there are both of them. C theta 1 is more informative. It's just that this is the theta angle. But if we, let's say C1 is the angle 1 or C theta 1. And S1, the sine of theta 1. And S1, 2 is theta 1 plus theta 2. That's it. Theta 1 plus theta 2, we call it C1. And this is a shorthand notation, quite complex and very simple and compact. And we get, this is forward kinematic. That's all, done. What does it mean? It means that if the angular value, if the joint vectors are given, if the joint variables are given, if Q is given, theta 1 and theta 2, if Q is given, we can simply find script X or T variable. But the inverse is not that simple. The inverse, we should, if these are given, this is some complex nonlinear equation, of course, algebraic equation, and we need some more mathematics to find the inverse problem. But we know that this inverse problem is also very valid and we can work on this. Is it hard? Forward kinematic, is it hard? Not at all. If you think about it as a loop closure, don't go through the way that Craig is representing this. It is much more easier to find the way it is really working instead of having an algorithm to find that. This is completely geometrical and conceptual, but unfortunately Craig and also in other books, as you see, they give some description for the links and the joins parameter, but I will give it to you, not to basically recommend you to always use them. Sometimes we need to use them if the robot becomes more complex. But usually in the exams, when you are using, just simple manipulation with hand, the conceptual or the inspection that you can get is much more effective, and you have to use both of them. What is an algorithmic approach? In an algorithmic approach, we would like to give a a method for a dummy person or for a computer. A dummy person, we don't have any dummy person in our class. All of our students are so intelligent, they don't need to think algorithmic to find it by inspection, but a computer is quite dummy. So it is some method that we can put together to represent the kinematic of any robot for a computer. I should add one sentence here. We need much of use of MATLAB and computer softwares to work with our cases in both in kinematic, in Jacobian, in dynamics, and in control. And this is a prerequisite of our course. If someone is not familiar with that, please get the premiere of MATLAB, and especially we will use symbolic manipulation in MATLAB or Maple. If you know Maple, it is much better. If you don't know Maple, no problem, but you should use symbolic manipulation. I have written some programs, not very professional. Of course, Dr. Taghirad is not that professional on MATLAB writing. Not that bad, but some programs. Our TA team will provide you with these programs, not just to use them, to see them as a motivation to write your own programs. And it is important, since if you have some programs during the class and during the problems and assignments, then you can use them in the exams, in the everything in what we are using in the evaluation forms that we would like to do. So please continuously write your programs and develop the programs that is required here. So we need MATLAB and symbolic version of the MATLAB that we will provide for you. In any case. So when we are using a algorithmic approach, we can use that. And there is a robotic toolbox in MATLAB. I don't like it that much. It is from Peter Cork, and I will provide that to you as well in the LMS of the system, that you can use that, of course, and everything else that you can find in the internet. In an algorithmic approach, what we are doing, we represent the most difficult links and in terms of algorithmic approach, and that's the way that I don't like. So the most difficult one I should define, and then you should use it for very simple robotic manipulator. What's the problem? What's the case for that? But anyways. And the problem is that, unfortunately, Craig, which is a very good book, has its own notation, which is different from all the other books and references. And since the Craig book is translated and used in Iran, many people in Iran just know the Craig book representation, which in my mind it is not good to do that. So the concept I will give you, the concept is the same, but I don't go through the Craig book. I go through the notation which is used in most of the books and most of the papers that you will see. Of course, some books and some papers are using Craig's, and you can go forward and forward. I will show you what is the difference and why Craig is a bit عقب افتاده. I don't want to say it in English because it is somehow given worldwide, but unfortunately I have also get the course with Craig book, and I guess many other of our TAs also have been taught from Craig book, although the Craig is very good book and Craig is very, very good roboticist. I don't like his notation here. But in any case, this doesn't matter really which one. For a link, we need 4 parameters. To represent a link, we need 4 parameters. One parameter is the length of the link. If we have a very simple link, the length of the link is the value of that we can measure from two joints. So a link is composing, as you see here, why I'm showing you with my hand, you can see it here. We have two joints at the end of the link. These joints could be either prismatic or rotary or revolute. So the length of the link, if it is very straight and very simple, it is the length of the link. It doesn't really need any definition. But if the link is very difficult, twisted, and so forth and so on, we call it the common normal line. The length is the common normal line between the axes. So how we define this for the link? We say that, consider that this is the link that we are considering. We have two axes, axis 1 and axis 2. The axes are the axis of rotation in the joint. So if we have rotary joint, the axes are the rotary joint are about them. If we have a prismatic joint, the axis of the joint is along the translation. And so we have these two axes, and then the length, we define it with the common normal form. These two could be parallel, so it is the simple length with the simple difference, the length between these two. But it could be somehow twisted, could be mutanafer. Then if this is the case, you find the common normal to that. Amud mushtarak, you find the amud mushtarak from that. This is the common normal line of length for that. And then it might have some twist as well. We call it the twist angle in a length. مقدار پیچش link. We call it twist. The twist angle is how much these two vectors are twisted. And usually these are sometimes 0 and sometimes 90 degree or minus 90 degree. And the angle we define, plus and minus in the frame in the next slide, as I showed you here. So these two are the prospect of length and twist of the link, how the link is basically designed in a robot. And we cannot have much more than that in terms of thing. The other thing is the offset and the angle. The offset and the angle, if this comes to two neighboring links, this is quite inherent for one link. Every link has a length or twist. Of course, many links have no twist and have only one length. The twist is 0 in many cases, but it could be having both of them. But these two other parameters, di and theta I, di and theta I, di and theta I, we have that one before, no? Yes, we had that one before. Look at that. Di and theta I was our q-axis. These two angles, we call it di and theta I, are from two neighboring joints and two neighboring links. So now consider another link is added here, and then you can find if we have a rotary joint, the theta is the angle between these two. This is the control parameter or the joint variable parameter. This is a varying parameter. If we have a prismatic joint, these two are, translating. So di is the variable that we are using. But if this is not, if it is rotary, but the joints are somehow have offset from each other, this offset can be considered as the di. So we have four parameters: ai, alpha I, di, and theta I. I don't go through how Craig is providing us because we don't want to use that, but we have this in the slide. But usually, most of the books find it quite easy. We can go through this, and this is the last part of my session here, and I will again continue from this point. We call it Paul convention. Paul convention is mostly used in many cases. What it does, it says, okay, consider link I. We have n link. Consider second one, fourth one, or whatever, link I. The notation we use is when we have link I, the first link, consider we have the first link. The first axis we start with 0 axis. This is quite natural. If we have the link 1, the first joint we call it 0 because this is the base. And unfortunately, Craig called it the first angle, and this makes it much more complicated. Just the simple misleading notation that Craig is using. Anyways, consider that we have link I, and we first define the axis of rotation from the joints. The joints could be either revolute or prismatic. If they are revolute, the angle that are about them, the axis that we have the rotation, it is the joint axis zi minus 1 and zi. And don't consider the red one. The red one are difference between the Craig and Paul. We will work only on Paul to make you life much easier for you. And this it is much harder for me, but much easier for you. You need only one representation to learn. If this is this zi is prismatic, just give the axis which is along the prismatic joint, not about. It is not perpendicular about. But if it is rotation, it is the axis of rotation as we see here. Then we start with the frames that we are assigning to this problem. The frame that we are assigning is, we have since this is I minus y joint, we have the z-axis joint already displayed here. So we have the zi and zi minus 1 from the rotation, from the angular values. Then we would like to give the x direction, xi and xi minus 1. How we can find the xi minus 1? It says that you should put the common normal, amud mushtarek. You have the common normal. You have two lines in the space. They could be either intersecting, they could be parallel, or they could be mutanafer, not parallel, not intersecting. In any case, you find the common normal. The common, if they are parallel, every line is common normal. So you use the middle line of the length, the way that it is. But if they are intersecting, if it is intersecting, the common line is just this point here. The common line is 0, the length is 0. And if they are not, it is general, there's only one single line which intersects these two in a common normal. We find the common normal. And when we find the common normal, it is interesting that we put this one as xi. We have zi and xi. We find xi in this way. What about xi minus 1? You should find it from the previous section, from the previous joint. So when x and z are found, then the y is very simple. X, y, z, you have a right-hand side coordinate. Of course, if Ali don't mind, we are using right-hand side coordinate like usual. Of course, in some books, maybe some people like left-hand side coordinate, then they have some other representation. But we use x, y, z. It is very simple. We have x and z, we find y. Now, since we have the axis, now we can define all the 4 parameters very easily. Let's see. Now, as mentioned, the common normal gives you the xi, and then you can find the plane, what you have here. Of course, it could have some limitations. We will show you in the example that we know. What we call AI. What is AI? AI is the distance from zi minus 1 to zi measured along xi. Since the common normal was xi, just the length of the common normal. That is simple. And usually we use positive length. We don't have negative length. Because we have put it this way, this could be the length of the common normal, the distance between zi minus 1 to zi in the direction of xi is, we call it zi minus, we call it ai. What is alpha I? The twist angle. The twist angle is the angle between zi minus 1 to zi. And the angle is measured along about xi. We say that we have here, and this is if they are parallel to each other, we have no twist. But if they are not parallel to each other, if they are this way or this way, these angles are changing. So there is an angle between these two, just put them together. And how we will measure when it is positive or negative, measure it about xi. This is quite simple. Since we are using ai, alpha I, we are measuring from xi. We are using ai, we are measuring about xi. And this is much easier in Paul convention than the Craig convention. And we just stick to this. So ai and alpha I is found from z-axis, and di and theta I are found from the x-axis now. Now we have x-axis here and here, as you see. This is two consecutive joints, two consecutive links. What is the angle between these? If they are rotary joint, this angle could be, changing. So this is a theta. We usually use positive theta to represent that. And the positive theta is about the z-axis. And if it is a prismatic joint, so they are sliding toward each other. Again, this di is changing, and the theta I is how they are, rotated along each other. We define it very simple. The di, the distance between xi minus 1 to xi measured along zi. If there is an offset, we find it in di. And the theta I is the angle from xi minus 1 to xi measured by about xi. Very easily to get that, and we will work on that in the next session, hopefully. You should learn the Denavit-Hartenberg problem. We call it Denavit-Hartenberg parameters. This is denoted by Denavit-Hartenberg. And I don't know why Craig has changed the way that Denavit-Hartenberg has proposed. Of course, the Denavit and Hartenberg proposed, the idea was that they propose only 4 parameters are enough to represent any link in the space. But in many of our cases that we will see, usually these angles and these lengths are very simple. They are either 0 or 90 degrees. We don't have some very sophisticated cases in industrial robots. But in nature, it is quite different. In nature, we have different angles, we have different offset. And it is very beautiful to see that, how optimized they are. Thank you very much for following me, and I hope that this part, this session was interesting to you and you could follow. If there is any question, please.
سلام.
If you don't, سلام. بفرمایید.
حسنی هستم.
چطوری علی جان؟
سوالم گمراه کننده است، منتظرم اینو کسی
طبق معمول میزنم. آره تو سوال تو بکن، منم میزنم تو برجتت. کاری نه دیگه، این قاعده ماست. ولی خوبه بچه‌ها زاویه منفی موارد رو هم میبینن از طریق شما. من همش مثبت میگم. یه کمی از اسکرو بد بگو اگر میتونی، اگر جرأتشو داری یه کمی.
من سوالم در مورد الان 2 تا دینامیت-هارتنبرگ معرفی کردید. یکی مال کریه، یکی مال پاوله که پاول کتاب‌های مختلف مثل اسپانگوتس و اینا معرفی شده. اگه من اشتباه نکنم یه دینامیت-هارتنبرگ سومی هم داریم، درسته؟
من ممکنه 4می هم باشه، من ولی زیاد آشنا نیستم باش.
پس اون که مودیفاید دینامیت-هارتنبرگ میگن مال خلیل و اینا همین پاله. یعنی مودیفاید الان خلیل
اصلا آره مودیفاید و اینا اشتباه. ببین در واقع کریگ چون یه کتاب خیلی پرفروشی بوده، با کریگ این موضوع پخش شده تو جامعه روباتیک. و خب متاسفانه کریگ به نظر من توی این مورد اشتباه کرده. یعنی البته اشتباه نکرده و خواسته اسم خودش رو در کنه اینجا. قبل از کریگ کاری که خود دناوید هارتنبرگ کردن و کاری که پال کرده و کاری که مثلا اسپانگ و نمیدونم سیسیلیانو و تسایی و بقیه استفاده میکنن به اصطلاح پاله. من خواهش میکنم این سوال البته خوبه برای بچه ها که بدونن ریپرزنتیشن های مختلفی وجود داره، ولی با یه دونش کار کنن کافیه. وقتی با یه دونه رو یاد بگیرید کار کنید، حالا ممکن تو پیپر دیگه یکی دیگه استفاده شده یه کمی فرق میکنه، یعنی ولی فرقش به اصطلاح این راحت تره. من احساس میکنم تعداد محورهایی که ما لازم استفاده کنیم توی پال به این ترتیبه. برای اگه مودیفای هم هست، اگه چهارمی هم پنجمی هم هست، فکر میکنم اونا رو الان وارد بحثمون نکنیم و شما با همین پال پیش برید. البته من اسلاید رو گذاشتم تو کتابتونم هست، اون یکی رو هم بخونید که اگر یه موردی ناچار شدید از کریگ استفاده کنید، خلاصه نگید استاد به ما نگفت. این چه استادی بود که به ما نگفت.
تشکرم.
خواهش میکنم. Any other question? Zahra, you don't have any question? It is quite amazing.
Hello.
Salam.
I don't have any specific question, just about the screw one. I think I need to further think about the part that it's projected, because then it's not one vector.
I don't have your voice quite well. Your question was about screw. What was about the... Can you repeat your question again?
It's in a previous slide, I guess.
Yes.
I don't remember what was that theorem.
Shall?
Yes.
Shall theorem. You don't remember shall. Shall is very good. Shall gardan, you know, very, very important. You have the shall gardan, you know, theorem.
Okay, now I remember it.
You remind me. I reminded you always, you know. Okay.
In the next slide, in 42.
Yes.
So here we have some projection as well, right? So it's just not one vector.
No, it is one vector. It is the projection of one vector. One single vector. Your question is very good. I know what do you mean. I don't want to answer right now because it might confuse the student. But no, you have only one vector, S0. S0 was the same thing that we have in the previous one. Here, as you see in this case, I'm not sure why my mouse is not working. Yeah, look at this vector. We call it POB with respect to A. We have the same POB with respect to A. We call it S0. This is one single vector. But why we put the D here, the projection here, to show you the behavior of a screw and bolt. You know, in a bolt and screw, when you rotate the bolt, the screw, the bolt will go up and down. Yes?
Right.
This up and down is this D, the pitch here. How much it goes up and down? It depends on the pitch of the screw. Some screws have very large pitch. If you rotate it one turn, it goes maybe 3 millimeters. Some of them are very fine. So if you rotate them, it goes only very little. And this is the D that we call it here. So that how much you are translating, you don't need to really have this as 0. You need that, but you can represent it with the D, the parameter, the projection of it to here, to just provide a screw concept to the idea. And that is why shall is important. You know, I didn't know that even a few years ago, maybe. I have taken the course, robotic course. I have done a lot of things. I know how this is being used in Jacobians, but I didn't know that Schall, the Schall-Gardan, has talked about it 300 years ago, almost 300 years ago.
Okay.
And it is very, very important. Here we have, again, rotation about an axis, translation along the same axis. And this axis is something super magical. We call it screw axis.
And the whole translation is encoded in that?
Yes. As you see, if we put the S0 and D with this relation, with only 3 parameters, the 3 parameters give you a translation motion. You know that the translation has 3 independent parameters. You have this here. It is hard for you because this is the first time you see that. When I see that, I thought, why other people don't look at the motion like this? It is much more easier to see this way. Please, change your point of view. چشم‌ها را باید شست. جور دیگر باید دید. بشورید لطفاً. چشم‌ها را باید شست. از سهراب عزیز. موفق باشید بچه‌ها. خداحافظ.